Hey guys, hope all of us are doing great. My name is Ernest, and this is Ernest's Sciences and Mathematics TV channel. So today we're going to look at the second bit of the laws of thermodynamics, and this is the second law of thermodynamics. Now, late in our discussion, we're going to look at also the concept of entropy and how we can be able to represent this particular aspect of entropy. Now, from our first law of thermodynamics, we had looked at a specific definition of this particular law, whereby we have said that we can be able to represent it in terms of an equation using that specific representation. Now, in this case, we have said that Q is representing the heat, the delta E is the change in internal energy, and W involves that element of work that is involved in this particular transformation. Now, in this case, we had said that from the first law of thermodynamics, we stated that energy can be converted from one form to another, but it can neither be created nor destroyed. And this, of course, formed the basis for the first law of thermodynamics, whereby we said that the total energy of a system must remain the same, although it may be changed from one form to another. Now, in the second law of thermodynamics, we're going to see a particular unique case which is going to assist us, of course, define this specific law, whereby we are going to, of course, create an emphasis on some specific aspect of change in energy. And in our description of chemical reactions, we said that some chemical reactions can undergo, or some either chemical or physical changes can undergo a process that we said to be reversible. For instance, if I give an example of a transformation between solids to gases, I can be able to represent this specific process using those reverse arrows, which indicate that this process can be able to be reversed, and hence it is referred to as a reversible process. So in this particular case, this is a melting, and the process from this liquid to gases is evaporation, and of course we're going to see a reverse process being described in some way. Now, in our description of this second law for thermodynamics, I'm going to use this just a simple illustration, whereby if we have a metal bar that is, of course, given using this illustration, and then one end of this metal bar is hot, so there's a difference in temperature between these two particular ends of a metal bar. We're going to see that naturally there's going to be flow of heat from this particular end towards this particular end for a cold part, whereby this particular temperature, or rather this particular heat energy, is going to flow until the temperature, of course, the temperature is going to attain what we call a uniformity. And in some cases we've talked about the concept of equilibrium, but I'm going to be particularly keen on using this specific term. So the temperature is going to be uniform at a particular instance, and therefore we will have said that the heat energy has flowed from this particular region to the cold one. And in this particular case, if we were to consider this specific forward process, and in some cases, if this process was to be reversed, we're going to see that the heat energy that has flown from the hot to the cold region is not going to be obtained in its total amount. So suppose we had the quantity of heat, initial quantity of heat that is flowing towards this forward direction given as Q. So the reverse energy, so this forward, the reverse energy, which is Q reverse, is not going to be equivalent to this. So therefore we can be able to conclude that there's not going to be a complete reversal that is going to be achieved from this particular process. This in an essence means that there are various changes which are going to take place in the system and its surrounding, which of course are not going to allow complete reversal. And this of course is going to form a basis for the second law of thermodynamics. Therefore, we can be able to state this specific law of thermodynamics, which is the second law of thermodynamics, that spontaneous processes or natural processes, which of course are going to occur without external aid, are going to be thermodynamically irreversible. So therefore, if we consider this one to be a natural or spontaneous process, and therefore it's going to be occurring in a manner that all the process, all the energy which has been used in this particular forward transformation is not going to be achieved in the reverse transformation, since some of the energies are going to be used, of course, or it's going to cause some changes in some of the parts of this system or its surrounding. Therefore, we can be able to see that this particular process is going to take place at a finite rate, whereby if I can be able to give an example of a process that we are referred to as spontaneous process. I've talked about the concept of radioactivity in some of my discussions, in some of the videos under radioactive activities or radiochemistry or physics. And of course, this is one of the processes that is natural and spontaneous. So this is going to form for us a basis of trying to describe some of the phenomena which is going to be experienced in this specific transformation. Particularly, I'm going to create an emphasis on this now that we have given an illustration of the second law of thermodynamics. So if you try to see this specific transformation from solid to liquid to gases, this basically is going to entail a phase transformation. Now, I've given an example of an illustration of the arrangement of molecules. For instance, if this one was to be given as such, we say that solids are made up of compacted molecular structure, which of course are going to be arranged in a particular uniform manner. And then liquids have got free molecules which can be able to move, but of course they are relatively compact as compared to, or closely together as compared to the gases. Now in this particular case, we're going to see that this uniformity is going to be disrupted as the transformation occurs from solids to gases. And of course, this particular kind of disorder is going to be, of course, forming a basis for the concept of what we refer to as entropy. So therefore, we can be able to refer to the concept of entropy as a measure of disorder, which is going to be realized due to the transformation of phases, which of course I've just given an illustration from this particular one that I've given on the board. So therefore, entropy is going to entail an increase in disorder of molecules that they change, that the phases change from this specific illustration from solids to gases. And also we're going to see other particular transformations which are going to, of course, entail the same aspect. So therefore, whenever we are having a system that is changing in this particular manner, we're going to see that there's going to be a change that is going to occur in a manner that is going to attain maximum entropy. Now, apart from the, I've given this specific, which is a change in enthalpy. So let me just give it in an. So this is the change in enthalpy. And I would say that enthalpy is a state function, which you of course are given as H is equivalent to E plus PV. And we say that this is a state function that is dependent on its current and not the history of that specific system. So therefore, we're going to see also that entropy is a state function, and it's going to form, of course, a basis for this particular essence of, and of course, it's going to form entropy is a state function, and it's going to form a basis for this particular processes of spontaneous or natural processes that I've just given an illustration above. And it's going to be represented using the symbol of S. So whenever we talk, just like we are represented enthalpy using H, entropy is going to be represented using the symbol of S. And therefore, whenever I'm going to mention the concept of a change in entropy, I'm going to use delta S given as such. So therefore, we can be able to move ahead and try to see how we can be able to give quantification or try to quantify this particular aspect of entropy, just like as this was the case for other aspects of enthalpy and molar heat capacity and other elements of thermodynamics that we had done before. So I'd mentioned that, of course, this particular process, which is going to entail the aspect of a transformation in the second law of thermodynamics, is going to be a process that is going to be spontaneous, and it's going to take place in a finite rate. So we can be able to measure these specific processes. So the change in this entropy can be illustrated using the symbol ds. I've said that S is going to represent entropy, and therefore it can be illustrated using that specific symbol ds. So therefore this is going to be the change in entropy, and sometimes I'm going to use this delta S. And for an infinitesimal change, we say that this is going to be accompanying the energy, so therefore we can be able to represent that change in energy of a reversible process using sigma q reversible. This REV is a subscript of q representing a reversible process that is going to entail the energy. So this is going to be the heat that is going to be observed when the change is carried out in a reversible manner. And of course we can be able now to describe this particular essence of the ds that is going to involve the heat that is going to of course change in a reversible manner over that absolute temperature given as such. So therefore this is going to imply the change in entropy which is going to be given as such. So if we can be able to describe this particular delta S from this particular description of the change in this particular entropy, by giving it as just as we have done for internal energy, we're going to see it's a transformation from one state to another by finding the difference between S2 and S1 for that particular example. So for us to find the total energy, we're going to do an integration between two specific range of temperatures for T1 and T2 of this particular value of Q. This is a sigma Q reversible over T given as such. So therefore this is going to create for us a description for trying to find the entropy of a system. And of course this is going to be forming a basis for us in trying to describe other subjects which are going to be of course accompanying this concept of entropy. Now in a summary form, I've stated that the second law for thermodynamics is going to give us an essence of trying to describe this particular essence of a system, whereby we say that if a system is going to take in some energy in a transformation or entail in a transformation of energy in a forward direction, the reverse reaction is not going to, of course, produce that specific amount of energy, since some of the energy is going to be used in causing changes in some part of the system and its surrounding. And therefore, this formed a basis for the second law for thermodynamics. And therefore, we said that this specific law can be stated as a spontaneous process, of course, that are thermodynamically reversible in character. And of course, we're going to see that they can be able to be described using a finite rate, which I said that can be represented using the energy that is going to be involved. And of course, the temperature, the particular temperature, absolute temperature. And from this, of course, I said that they are going to form a basis for what we call the concept of entropy. And entropy, as we said, is a measure of disorder, which is going to be represented using an initial of S. Now, the change in entropy can be, of course, represented using this particular ds, and therefore, the total change, which we had said can as well be given in terms of delta S given as such. And then we said that we can be able to give a specific example of a change in entropy of an infinitesimal change using the delta Q reversible given as such, whereby we said that there is a relationship between the entropy, the change in entropy and Q reversible, in a sense that it's going to be a ratio, the ds is going to be a ratio between Q reversible, delta sigma Q reversible over the absolute temperature given as such. And we can be able to give an overall representation using that integral equation of this specific nature in representing entropy. So catch us in our next video as we're going to look at the concept of entropy in details, and especially when we're going to consider some aspects of what we had said for pressure, volume, temperature, mass, and the composition, which basically we said are going to be some of the variables and conditions which are going to affect these particular states of thermodynamics. So that is it for now, guys. Bye, God bless you. Catch us in our next video.